There is a hull geometry that reduces hydrodynamic drag by up to 30% compared to the conventional displacement hull shapes that dominate recreational and commercial boat manufacturing today. It does not require exotic materials, it does not require a larger engine, a more powerful drivetrain, or any propulsion system modification whatsoever. The fuel savings it generates are not marginal efficiency gains measured in single percentage points. They are documented, independently verified, and reproducible across vessel classes, ranging from small recreational runabouts to commercial fishing boats to offshore patrol craft. And the naval architecture principle behind it has been understood, tested, and published in peer-reviewed hydrodynamic literature since the 1930s. A commercial fishing operator in Norway switched 2 vessels in his fleet to this hull geometry in 2019. His fuel costs across those 2 vessels dropped by 28% in the first full operating year. Not through engine replacement, not through propeller optimization, not through any modification to the mechanical systems that his maintenance budget and his parts supplier relationships depended on, through hull shape alone. The water moving around his boat simply encountered less resistance, and less resistance meant less fuel burned per nautical mile traveled for the remaining operational life of those vessels. The global recreational boating industry generates $42 billion annually. The commercial marine fuel market processes hundreds of billions more. Both industries share a single structural dependency that the hull shapes currently in production, currently in dealer inventory, currently represented in the tooling investments of every major boat manufacturer on Earth, remain the shapes that consumers accept as correct, standard, and inevitable. A hull geometry that cuts fuel consumption by 30% without any mechanical modification threatens every assumption those tooling investments were built on. And a $42 billion industry with decades of sunk cost in conventional hull molds does not quietly absorb a 30% fuel efficiency revolution. It gets very quiet about the research and very loud about the accessories. This is the story of the wave-piercing X-BOW and its hydrodynamic relatives, the hull geometries that naval architects have been documenting for nearly a century, that competitive offshore racing has been exploiting for decades, and that the recreational boat manufacturing industry has spent the better part of that time ensuring never appeared as a standard option in a showroom that sells fuel, maintenance contracts, and engine upgrades alongside the boats that need them. Right here, before we go further, if this is the first time you are hearing something that should have been common knowledge for decades, that tells you everything about who controls what gets taught. Subscribe to Lost Tech Vault and hit the like button now. Every video we make is a door that someone paid to keep locked. We open them anyway. Ring the bell so you never miss one. To understand why hull shape determines fuel consumption more decisively than engine power, you need to understand what a boat is actually fighting every second it moves through water, because the physics of hydrodynamic resistance is the most consequential and least discussed variable in the entire recreational boating industry. When a hull moves through water, it encounters 3 distinct forms of resistance. Frictional resistance, the drag created by water molecules moving along the wetted surface of the hull. Wave-making resistance, the energy consumed creating the bow and stern wave system that every displacement hull generates as it moves. And form drag resistance created by the cross-sectional shape of the hull pressing against and separating the water column ahead of it. At low speeds, frictional resistance dominates. At the moderate cruising speeds that recreational and commercial vessels spend the majority of their operational hours at, wave-making resistance becomes the dominant energy consumer, and this is where conventional hull geometry is catastrophically inefficient in ways that the manufacturing industry has never had financial motivation to address. A conventional blunt bow, the rounded, flared entry shape that defines the majority of production recreational boats, meets the water column ahead of it with a geometry optimized for interior volume, for deck space, for the appearance of strength and substance that boat buyers in showrooms respond to emotionally. It is not optimized for hydrodynamics. It creates an enormous bow wave at moderate speeds that the hull must continuously climb, consuming fuel not to move forward but to maintain position on a wave of its own creation. Naval architects call this the hull speed limitation, and for conventional displacement hulls it represents a fundamental energy ceiling that no engine upgrade can permanently overcome because the problem is geometry, not power. The X-BOW concept, a sharply raked near-vertical bow entry that pierces the water column rather than riding over it, was documented in formal hydrodynamic testing by Dutch naval architect Kees Mooij in the 1990s, though the underlying principle appeared in experimental vessel designs as early as the 1930s. The geometry works by fundamentally changing the relationship between the hull and the wave system it creates. Where a conventional bow lifts and displaces the water column ahead of it, spending energy on vertical water movement that contributes nothing to forward progress. An X-BOW geometry divides and deflects that water column laterally at the waterline with minimal vertical displacement, dramatically reducing the energy required to maintain any given forward speed. The wave-making resistance reduction documented in comparative tank testing between conventional and X-BOW geometries at practical cruising speeds ranges from 20 to 35%, depending on hull length, displacement, and speed regime. That resistance reduction translates directly and proportionally to fuel consumption, because the engine is doing less work per nautical mile to overcome drag that the hull geometry was creating unnecessarily. The Norwegian offshore supply vessel industry began adopting X-BOW geometry in the early 2000s after Ulstein Group, a Norwegian naval architecture and shipbuilding firm, developed their X-BOW design and documented its performance in commercial operations. Vessels operating in North Sea conditions reported fuel savings between 20 and 30% compared to conventional bow designs operating the same routes at the same speeds. Ulstein's X-BOW went on to be adopted across dozens of offshore support vessels operating globally. The commercial marine industry, where fuel costs represent 40 to 60% of operational expenditure and where a 30% fuel reduction translates directly to competitive advantage measured in millions of dollars annually, paid serious attention. The recreational boat manufacturing industry paid almost none. The reason that a tension gap exists is not technical. It is not because X-BOW geometry presents engineering challenges that production boat manufacturers cannot solve. It is because production boat manufacturers have between $2 billion and $8 billion in existing hull mold tooling, representing conventional bow geometries that they have not finished amortizing. A new hull mold for a recreational boat model costs between $500,000 and $2 million depending on size and complexity. A manufacturer with 40 active hull molds in production has between $20 million and $80 million in tooling investment that a geometry revolution makes obsolete. Beyond tooling, the dealer and service network that supports recreational boating is structured around the fuel consumption, maintenance intervals, and engine stress profiles of conventional hull designs. A boat that uses 30% less fuel per hour is a boat that visits the fuel dock 30% less often, strains its engine 30% less severely, and extends its service intervals proportionally. The marina operators, fuel suppliers, and engine service technicians whose businesses are built around conventional hull consumption patterns have no enthusiasm for a hull geometry revolution that their customers would benefit from enormously. Competitive offshore powerboat racing, the one corner of the recreational marine world where performance data drives decisions and manufacturer marketing budgets do not, has been exploiting wave-piercing hull geometry for decades. Competition vessels running X-BOW and wave-piercing entry designs consistently outperform conventional hull competitors at equivalent power levels in offshore conditions because the physics is not negotiable at racing speeds and racing distances where the cumulative drag penalty of conventional geometry becomes unmistakable. The technology demonstrably works in the most demanding test environment available. It just does not work its way down to production recreational boats because the production recreational boat industry is not structured around the physics of water resistance. It is structured around the economics of showroom appeal and service revenue. I want to be precise with you here because this story deserves accuracy alongside its frustration. X-BOW and wave-piercing hull geometries deliver their largest efficiency gains in offshore and open water conditions at moderate to higher cruising speeds in chop and swell. In flat calm water at low speeds, the efficiency advantage narrows compared to well-designed conventional hulls. Interior volume in an X-BOW design is reduced at the bow compared to conventional flared entry designs, a real trade-off that affects accommodation space on cruising boats where interior volume matters to buyers. And the visual language of the X-BOW, dramatic, angular, aggressive, does not suit every market segment or every buyer's aesthetic preference. These are genuine engineering and commercial trade-offs, honestly stated. But for the core use case, a recreational or commercial vessel traveling at moderate cruising speed through open water for extended periods, burning fuel at a rate that its owner pays for continuously across the operating life of the boat, the hydrodynamic case for wave-piercing hull geometry is documented, independently verified, and commercially proven across decades of offshore commercial vessel operation. The Norwegian offshore industry adopted it because fuel is 50% of their operating cost, and physics is not negotiable when margins are measured in millions. The recreational industry ignored it because hull molds are expensive, dealer service revenue depends on fuel consumption, and showroom buyers respond to interior volume and bow flare that look substantial from the dock. Kees Mooij documented X-BOW hydrodynamics in the 1990s. Ulstein Group proved it in commercial North Sea operations in the early 2000s. Competitive offshore racing has exploited wave-piercing geometry for decades. Tank testing at naval architecture facilities across Europe and North America has reproduced the 20 to 35% drag reduction numbers consistently across vessel classes and speed regimes. And the $42 billion recreational boating industry continues building conventional blunt bows optimized for showroom appeal, interior volume, and the fuel consumption rates that keep marina operators, fuel suppliers, and service technicians profitable on the backs of boat owners who have never been told that the shape of their hull is consuming 30% of the fuel their engine is burning unnecessarily. The water has not changed. The physics has not changed. The naval architecture literature documenting the geometry that works better has been publicly available since the 1990s. The hull molds have. And in a $42 billion industry, hull molds are what determine what shape your boat takes, not the physics of the water it moves through. Subscribe to Lost Tech Vault. Share this with someone paying for fuel that a different hull shape would have saved. The next vault opens soon, and what is inside it is heavier than this one.